Hello everyone. Today we'll talk about contrastive loss. From the start, there is some confusion because there are two different losses people call contrastive. The first one, published by Jan LeCun's team in 2006 in the paper Dimensionality Reduction by Learning and Invariant Mapping, is, from my point of view, the true contrastive loss. As usual, the title sounds complex, but it's just about reducing dimensions of the data with machine learning model. The second one came from Geoffrey Hinton's group, and it's about a special case of training neural networks using augmentations. First, let's look at loss number one. Let's say we need to create a classifier for some dataset, but we don't want to use traditional cross-entropy loss. Why? Think of cross-entropy loss as a way to train our network to output a sparse, or to be more accurate, semi-sparse classifier in a space where the number of dimensions equals the number of classes. In that space, we have one basis vector per class. It's all nice, but sometimes it can be beneficial to use something different. A space with n number of dimensions, where n is not equal to the number of classes, and usually it is much less. Remember, the paper mentioned had dimensionality reduction in the title. Why would we want to convert inputs to a space with fewer dimensions? The most probable case is if that we want to save compute and memory to, and encode, for example, a person's face or voice as a single vector. Imagine we have a neural network that converts an image from the MNIST dataset into an n-dimensional vector. One way to train such a network is with contrastive loss. It's called contrastive because we train the network by comparing pairs of samples. Small note. In papers, this setup is usually referred to as a Siamese network with shared weights. But don't be fooled. It is actually a single network. We just pass two images through it simultaneously. As a result, each image is projected to a point in the n-dimensional space. With 2 points, there is a distance between them, and we need to train our network to modify the coordinates of the points. If both samples belong to the same class, we need to decrease this distance and pull them closer to each other. If the samples belong to different classes, we need to increase this distance and push them apart. In this way, we'll group the outputs from the same class around some point in space and form a cluster. Now, let's write it down in a simple way. For 2 points from the same class, we'll call this a positive pair, we need to decrease the distance. Let's call it positive distance. For points from different classes, a negative pair, we need to increase the distance. Let's call it negative distance, though it's not literally negative. Problem here is that we expect our loss to eventually to be close to zero, but the negative part is increasing. The first idea that comes to mind is to compute 1 over the negative distance. This isn't the best choice because 1 over the negative distance will reach 0 only if the distance is infinite, which would push points from different classes apart indefinitely. Instead, we just need to push them apart far enough. The paper proposed using the max of 0 and some margin m minus the negative distance. Let's see. If the negative distance is increasing, then the margin minus the distance will, on the contrary, decrease. But it will also decrease indefinitely, making our loss less than 0. That's why we add the max function to ignore the negative case. And now let's compare what we've got so far with the original loss equation. Notice something similar? There is a positive part and a negative part. If both images are from the same class, then y equals 1, zeroing the right side of the loss. For the case of different classes, y is 0, and it zeroes the left side. That's the idea of contrastive loss. We either pull positive together or push negatives apart. Except somehow there is also a power of 2 and a coefficient of 1 over 2. Without them, the loss function is very simple. Its value, or the force it uses to push or pull samples, is equal to the distance for the positive case or the margin minus the distance for the negative case. It's completely linear and straightforward. The problem is that during training, our networks will often say, "Screw this, I'll just collapse all outputs into a single point, 0. If all outputs are zeros, all distances are zeros too, and our loss will get stuck at half of the margin because it's the mean of all losses. To deal with it, we introduce nonlinearity. The simplest option is just to square both sides. The authors explained it this way. Squared loss is very similar to the potential energy of an elastic spring. The derivative of such loss with respect to the weights W of our network is similar to the equation of the force applied to the spring. In practice, we can skip 1/2 because we scale gradients using the learning rate anyway, but it makes derivative even prettier. Thus, we can think of our loss as a bunch of springs looking for a state with the smallest amount of potential energy. The final part of this video covers the second loss function, but to be honest, it's a bit dry. If you're not particularly interested in that, I'd recommend skipping it to save some time. And now something completely different, second loss. This one is specific to the paper, so instead of digging deeper into it, let's just deconstruct it. It looks similar to cross entropy, a combination of negative log likelihood and softmax, but we have a sim function here, which is cosine similarity. You can watch the previous video on this channel about it. Imagine we have a set of n images, such as faces, pictures of dogs, or sound spectrograms. We apply two different augmentations to each input, such as rotation, scaling, or erasing, and pass them through our network to get two n outputs. Now, instead of selecting positive pairs based on class similarity, we consider a positive pair to be one single input with different augmentations applied. All other samples are considered strangers, so any pair built using them is a negative pair. Our loss function contains the positive pair in the numerator and all pairs, both positive and negative, in the denominator, except pairs with themselves. The minus log here equals 0 if the fraction is equal to 1. Since e to the power of x is monotonically increasing, to make the fraction close to 1, we need to maximize our exponential expression for the positive pair, while minimizing all exponential expressions for the negative pairs. This will make our fraction as close to 1 as possible. Cosine similarity is a cosine of an angle between two vectors, and bounded between -1 and 1. And since e to the power of x is increasing, we need to push cosine similarity to 1 to maximize exponential expression, and to -1 to minimize it. Cosine is 1 when angle between two vectors is 0, and -1 when vectors are pointing towards opposite directions. So our loss is pushing angle between two positive, augmented outputs towards 0, and angles for negative pairs towards 180 degrees, opposite directions. In a way, this is also contrastive loss, since it works with positive and negative pairs, pushing and pulling them apart. That's all for today. Thank you for staying till the end, and see you next time. And don't forget to comment and subscribe. Bye bye.